So yeah, good morning, good afternoon, and good evening to everyone. Thank you very much to MLT today. All right. I'm going to briefly introduce our presenter today. So today we have Joshua Owoyemi, sorry, and he's an AI engineer at Elix in Tokyo. He holds a PhD in system information science focused on machine learning applied to robot manipulation. And his research interests are machine learning, computer vision, and semi-supervised learning. So with this, I'm going to give the floor to Joshua.
Okay, thank you so much. I
Perfect. We
guess you
can
can
hear
see
you. Yes, we can see, we can hear. Yeah.
great. Thank you for the opportunity to share the paper. Yeah, the paper is image is worth 16 by 16 words and transformers for image recognition at scale. So there was this paper was first on ArchiveX, but now I think it's been accepted at the ICLR conference this year. So it's a very recent paper, and I'll do my best to explain my understanding of the paper. Yeah, so show you first the outline, what I really want to go through in this paper. I'll first give a brief general introduction of more like a summary of the paper from the beginning so we know what to expect, and just kind of also trace the intuition from MLP to transformers. And I know that MLT Tokyo has been working on attention for the past few months. So just as a way of completeness, I'm going to try and just do a quick recap on self-attention, which is like the building block for this paper. Then we'll go into what makes the paper, and then I'm going to talk about some experiments and results from the paper. Yeah, so first thing is what are the claims of this paper? What are the things that they want to achieve through the paper? And first thing is they want to say that CNNs may not be necessary, or at least are not necessary for this kind of tasks, such as image image recognition, or in this the specific task in this paper is image classification. And again, through their results, they're able to show that attention-based network can result in substantially fewer computations. So in other words, if we do away with CNNs, we can also gain computationally uh, using transformers. Yeah, so the paper is not very technical. After reading through it, there are no new ideas in the sense of like the theory or the mathematics. It's just an application of the attention is all you need paper into the image space. So why is this paper important? So the thing is, it basically challenges the inductive bias of CNN. So we know that CNNs are very popular in the image space and basically the de facto building block for so many image recognition tasks. And so they challenge this inductive bias by just doing away with CNN and replacing that with a transformer network. And also, I think this also opens up alternative perspectives to solving vision-related tasks. So as we all know that CNNs are very popular, but what happens if we do not want to use a CNN, or for any case, something better than CNN is out there? So this is one importance of the paper. And basically the single main idea is, let us try to apply transformers, which is a language, a natural language processing centered network to a vision related task. How is this going to be? Is it going to be good? Is it going to be bad? And how do we do that? How do we implement this kind of idea? So that is basically the main idea of the paper. So now I want to kind of trace the intuition, how we've moved from like MLPs to transformers. We know that MLPs are theoretically, they are good nonlinear approximators, however, they're inefficient in implementation and practice. So for example, if you would want to classify this image, we know this is a very popular sample in the in this data set. you would want to connect each of the pixels to each node or each single unit in the MLP. And if you have to do that, you realize that the computation gets more and more, um, it increases as you increase the image space. So which brings us to the inductive bias of CNNs, in the sense that we don't have to connect each of the single pixels. We can actually try to convolve a certain kernel, which is what we're going to learn in this case. The weights of the kernel will interact with the pixels of the features in a particular layer to give us the output of the features in the next layer. So this did away with the one-to-one connection from each of the pixels in the first network, which is the MLP. And now we go to the intuition of the transformer layer. We can also try to think of the image as a sequence, or if we would like split the image into a sequence or a patch, a sequence of patches, which would become the input into this kind of network. And the reason is that we are kind of doing away also with the inductive bias of having to preserve the translational dependence of the pixels in the image, and just treat it as one single input feature. And the naive approach, or the naive application of self-attention, would be to connect each pixel and attend and see the relationship of one pixel to another. But you would also realize that that would bring us back to the MLP idea, which is basically treating one pixel as an input feature. However, if we decide to kind of group together all the input features, such as these pixels, we can find the relationship between, or some kind of dependence between each of the patches in the image. And what you find out is that at this stage, what we're doing basically is trying to extract features, useful features, using this kind of networks. And we still cannot do away with MLPs, because they are very good function approximators. And so if we are able to extract very useful features using these approaches, we can later now use the MLPs to aggregate our features into the final output that we want. So this is somewhat like the mindset of moving from one model to another. So now to recap on self-attention. Self-attention, or attention in the first place, is basically a mechanism that helps to build and quantify interdependence. So if you have, I'm going to first use the language-based approach, where, for example, you want to translate from one language to another. It means you want to find the dependence of some inputs, the items in a particular sequence that contributes to the output in the other side, or maybe another word in the other language. And now talking about self-attention, you can compare between a source and a target. That is, if you're not doing the self-attention. But in self-attention, all the interdependence is within the elements of the source itself. So in this case, you have the query. I'm going to talk about this later, but you have the key, query, and the vector, and the values, which are mapped from the input space. And you do some kind of interaction between these three mappings in order to find the dependence of the inputs with each other to give us a particular output. And this has become the de facto standard in language processing tasks. So for example, if you would have like a translation problem where you want to say, you want to translate the quick white fox, which is in English, jumps, to another language, which is Yoruba. You would want the words that are very similar, or that contributes to each other, to give a word on the other side to contribute more weight to the prediction of that word in the translation. And so this is why attention is very important, because it now weights the input sequence in the order of importance and use that importance to predict an output. And so talking about what happens in the self-attention layer, what we do first is to map these input sequences or each of the elements in the input sequences into what we call the query, the key, and the value. So you can think of the query as a task. What do we want to achieve? And the key are the relevant features or the features that are important to achieving this task. And the value is the relevance of the key on the queries. So how does the key match, or what is the similarity between the key and the query that is able to give us the output that we want? And the first thing we do is compute a weights vector, which compares, which is like a pairwise similarity between two elements of the sequence and the in the respective query and the key representation. After we get the weight vectors, we can now obtain a context vector, which compares this similarity with the value of that input space. And that will give us the output on the output of that self-attention layer. So basically, a self-attention layer is a function of the input space that is mapped to three different weights. Now, what we're trying to do here is basically learning the parameters, the weights of the key, weights of the query, and weights of the values, and how the interaction of this weight gives us the interaction of this weight actually gives us the output that we want. So this serves as a building block now in the transformer model. And this is the model used in attention is all you need paper. What you find is basically you have two parts. Basically, you have an encoder and a decoder. So an encoder is basically trying to extract features from the input, and the decoder will also extract features from the target that you're looking at, and trying to compare or combine the features from the target to the with the features from the inputs to give an output. Now, when it comes to the image-based problem, we do not actually need the decoder part, in the sense that the problem is not a sequence-to-sequence problem. It's basically a sequence-to-class problem. It's a classification problem. So we do not need to do, at least according to this paper, we do not need to do any kind of decoding, because the input also is the same as a source, and the target is the class of that particular source. So we basically just reuse the encoder, the transformer encoder, as the basic building block for the image task. And so the task in this image recognition problem is basically, if we have an image, we would like to transform the input, this image input, in a way that is useful for the vision transformer, or in this case, the multi-layer, multi-head self-attention network. And also that will now give us the class at the end. However, the vision transformer cannot work directly on images. So, and it needs a sequence of token embeddings, basically a sequence of vectors, which those are the inputs that are expected by the vision transformer. And how do we kind of transform this image into a set of input features that is useful for the vision transformer? This is basically the idea of the paper. So the first thing we do is to split the image into patches of the same shape. So in this case, we have an image, and in this particular example, it has been split into 9 patches. In the paper, they have 14 by 14 patches. They have 16 by 16 patches, of course, which is the title of the paper. And so when we split this, we still cannot use it this way. Then we flatten the patches into a sequence of 1D vectors. And so if you think of this image as if this patch has a 7 by 7 as a 7 by 7 dimension, which also has 3 channels, that would be 7 by 7 by 3 1D vector. This is still very large input space. So what we do next is we would map this input patches, or this 1D vector, into a size D latent vector, which is by using a trainable linear projection. So what that means is basically using an MLP, very small MLP, multi-layer perceptron, and the weight is shared between all the input space to give us the size D latent vector. That is now the input into the transformer encoder that will be used for the classification. And so this is called the patch embedding. One more thing is that for a sequence to sequence problem, you have like an input space of maybe m vectors, and you have an output space of m vectors or m classes basically. However, since we are doing a sequence to class, we would need to append a learnable embedding for class to the sequence. So which means that we are not getting output from each of these patch embeddings. The output is basically from this class embedding. And what the class embedding is doing based on the attention, self-attention idea is to aggregate the weights from each of these patch embeddings inside the transformer encoder and decide which class are we going to get at the end. So this needs to be added to kind of give us the class at the end of the model. Next is we would need to add position embedding. So also in the language model, you need the position of each word in a particular sentence is very important. The same thing is true for images. The spatial location of each patch is very important. If you were to jumble the spatial location of each of this patch, it would, humanly speaking, it would be impossible to kind of understand what is happening in the image. And I think also for the model, it would be very difficult to, it would be challenging to actually scramble this kind of random positioning. So this is why the position embedding is very important. The position embedding basically just adds a set of vectors to our patch embeddings in order to learn the position of each of the input sequence. So therefore, the transformer encoder is basically an alternating layer of multi-head, self-attention, and MLP blocks. So I talked about self-attention before, but the multi-head variant is that you would have a self-attention layer, but you would now have, like, in parallel, more heads in that same layer. So you can now aggregate or concatenate the output from all the multi-heads into one in order to pass into this multi-layer perceptron network. And so also we would add a normalization before each block in order to control the magnitude of the features in each block, so that the features do not blow up. And we can also borrow the idea from residual connections by this would just basically help us to have many layers of the network stacked together without losing, in order to minimize the problem of diminishing gradients in the network. And you can have this as many times as possible. However, in the paper, which is almost the same as what you have in the attention is all you need paper, you have only 6 layers that was used. So, and finally, you would have the output from this transformer encoder and transfer it pass it through an MLP, which now gives us the class of the classification of that image. So it's very necessary to understand that there are 2 stages. One stage you fine tune. I'm going to talk about this later. One stage you pre-train, and the other stage you fine tune. So in the pre-training stage, you use this one hidden layer MLP, and in the final stage, which is just fine tuning, you can replace that with a linear layer during fine tuning. So how did this perform in real world? So basically, in the paper, the vision transformer is pre-trained on large data sets, and like I said, the pre-trained ed is replaced with a D times K feed-forward layer. So the dimension, the D is the dimension of the input space, which is the dimension of the self-attention network of the self-attention outputs, and the K is the number of classes that we are trying to predict. And there are three large networks, three large data sets that was pre-trained on. One is the ImageNet, and the second is the ImageNet 21K, and the third is the JFT 300 million. So it's necessary to talk about this, because this is one of the key points that actually made the vision transformer maybe desirable, in the sense that it's able to learn from very large um, data sets. In this case, one thing to note is that this JFT dataset is a proprietary dataset, which is only accessible to Google. So you would see why this is very necessary, very important. And again, they said that VIT, the vision transformer, can handle arbitrary sequence of length up to memory constraint. So there is a step that was not really explained in the paper, which is if you are to transfer a pre-trained network to a new network and you're already trained on a particular resolution, how do you do the position embedding from one resolution to another? So they said that you can basically interpolate a new resolution to the new position embedding to the old, to the pre-trained position embedding, but there's not so much detail on how this is done in the paper. So however, the point is that when you pre-train, the position embedding may no longer be meaningful if you're transferring to a new resolution entirely. And so this is the first result from the paper. So you need to note here that the model was pre-trained on the JFT 300 million data set. And it was, of course, it outperforms the ResNet-based model, which is the CNN, the classical CNN-based models. And they also claim that you need substantially smaller computation and resources in order to train it. However, if you look more closely, you would find out that this edge is only because of the vast number of data set that it was pre-trained on. So the 300 million data sets from Google. And to compare with the ResNet, the only thing is that ResNet could not train much better, even when introduced to more data sets. So here you find out that when you pre-train with smaller data sets, which is kind of ironic, because if you say small data sets, and if you say like 14 million images, a small data set, I think in this case, I wouldn't say that it's really small data set. In any case, from the comparison, ResNet kind of outperforms the vision-based networks when you pre-train with ImageNet and ImageNet 21K, which both are up to 15 million data samples actually. Not until you pre-train with as much as 300 million, that is when you see the performance gain over ResNet. And you can also see that in this second result here. And also as per the computational difference. So for the same performance, they showed that the vision transformer is able to achieve the same performance with lower computation resource and lower computational budget compared to the ResNet, which I think it's good if you're Google and you don't want to spend so much money on computation. Yeah. So now talking about the positional encodings, positional embeddings, there is no significant difference, because you could do a 1D positional embedding and you could also do a 2D positional embedding by just maintaining the spatial relationship between the patches of the image. And according to them, there is really no difference. And finally, the model is able to learn to basically encode the distance within the image and the similarity to the positions of the embedding. So what you see here is that each of the embeddings is able to encode its own relative position in the image, which means that whether you use a 1D or 2D, the model is able to actually understand where that particular patch is coming from in the image after training. And this using different hyperparameters, the results are the same. Yeah, so final point for me is that I think transformers still lack some inductive biases inherent to CNN, such as translation, equivariance, and locality. And therefore, they still do not generalize well when trained with insufficient amount of data. Well, the word insufficient amount of data is still debatable because how much is sufficient anyway. But what you find out in this paper is that the more data you have, the more edge the vision transformer would probably have on the ResNet-based models. And there are still so many unaddressed challenges in the sense that how do you apply this kind of model to other vision tasks such as object detection or segmentation and things like that? And how do you do large-scale self-supervised pre-training? Because of the, so to say, the relaxed inductive bias of the vision transformer, we might not be able to apply it in the same way as you do with the popular ResNet models in these other tasks without a real redesign of the network itself. And so that will bring me to the end of the talk part. And it's a really short paper. Not so technical, but I think that's able to just give us an idea of what the paper is all about. Thank you.